in our side. We try to do all the best, and as a general chair of 2020 PEMC conference, I'm very happy that I can meet all of you here. I'm quite sad that we can meet only in virtual form, but as a scientific society, we should adapt quickly for any situation. So I hope we adopted already to meet during this virtual conference. And in order to add some local accents to our meeting, I would like to invite you for a short music performance, which will be presented by a famous local team having almost 70 years of history. This is the Silesia Dance and Music Ensemble. So please enjoy this performance now.
On behalf of Stanisław Hadynasz, Śląsk Song and Dance Ensemble, we would like to welcome all participants of the International Conference on Power Electronics and Motion Control, Gliwice 2021.
Congratulations on the 50th anniversary of the PEMC conference series. We would like to invite you to an accept from the gala program of the Śląsk Ensemble, the ambassador of Polish culture.
Poszła Karolinka do Gogolina. Poszła Karolinka do Gogolina. A karliczek za nią z flaszeczką wina.
A karliczek za nią z flaszeczką wina.
Nie goń mnie, karliczku, czego po mnie chcesz? Nie goń mnie, karliczku, czego po mnie chcesz? Jak ci już powiedziała, nie wydać ci chciała, sam to przeco wiesz.
Jak ci już powiedziała, nie wydać ci chciała, sam to przeco wiesz.
Wróci Karolinko, moja łaska. Wróci Karolinko, moja łaska.
Już się już nie wróca, bo jest na moście. Już się już nie wróca, bo jest na moście.
Wróci Karolinko, co idziesz wstecz? Wróci Karolinko, co idziesz wstecz?
Nie odpowiem tobie, po swojemu zrobię, to nie twoja rzecz.
Nie odpowiedziałem, synko odwieszałem, mój okraka rzecz.
Szła dzieweczka do laseczka, do zielonego, do zielonego, do zielonego. Napotkała myśliweczka bardzo szwarnego, bardzo szwarnego, bardzo szwarnego.
Myśliweczku, kawaleczku, bardzo ci rada, bardzo ci rada, bardzo ci rada. Dałabyś ci chleba z masłem, ależ go zjadła, ależ go zjadła, ależ go zjadła.
Okay, thank you very much for listening. Hope you enjoyed this music. So now it's time to show you the structure of our conference, to show you ideas for the program. So I will share with you my screen and show you. I'm sorry. Okay. Hope you see the screen at the moment. So the first things which I wanted to present you is our schedule. Most of you know this table very well. So this is time to say a few words about the structure of the conference. So at the moment we are at opening ceremony. Just after that, we invite you to the keynote address given by Professor Johann Kolar from Switzerland. And after that, we have, as every day, 2 blocks of parallel oral sessions. In between, we will have second keynote address given by Professor Mariusz Malinowski. And at the evening, we would like to invite you for a special ceremony, special meeting, which is welcome online party. Of course, this is not the same, it is still virtual party, but hope it will be good opportunity to make kind of integration and informal discussions. Tomorrow morning, we start 8:30 Central European Summer Time with parallel oral sessions. After that, we invite you for special celebration. It will be started by keynote address given by Professor Zdeněk Peroutka from West Bohemia University. And after that, we will celebrate 50th anniversary of our conference series. Special presentation is prepared by Professor Marian Kazimierkowski and Professor William Fetter. Afternoon, we have second block of parallel sessions. And after that, Professor Jean Levesque from University de Lorraine will present a keynote address. After the keynote address, we would like to invite you for students and young professional activity, followed by industry-oriented round table. The third day, we start again with parallel oral sessions. And after this regular part, we can listen keynote address given by Professor Pavol Bauer. And after that, student and young professional competition will take final competition, final presentations. Afternoon, we have the last block of parallel oral session, and final keynote just before closing ceremony will be given by Professor Peter Korondi. Every parallel session has 4 tracks, 4 sessions is included, and you can select proper. In order to join virtual conference, you have to manage this, let's say, online tool like this participant portal. So I would like to present some important features at the moment of this portal. So first, in order to join the session, you have to log in to the system. So when you go to mine webpage and clicking participant portal, you will be asked to log in to the portal with your data which you provided during registration. At the top of the screen, you have a conference announcement. So please read if something new, important is announced, some changes, important things will be presented here. The second section is a searching tool. You can insert here any part of participant name or paper title and find in the conference program. The timetable, which I presented, has interactive form, so you can click any interesting place on the screen and go directly to the session in the program. If you have any troubles and want to ask something to conference staff, please contact the help desk. Here you can also find instructions how to use conference tools, how to behave as participant, author, and session chair. Okay, so another tool is virtual conference lobby. In this lobby, you can enter the session when you want to discuss with your colleagues, when you want to create mutual discussion. So this lobby is waiting for you anytime from 9 morning till 6 p.m. Let's say my time zone of conference. And let's go to the main conference program. So here you can find description of all sessions provided during the conference. And on the left side, you have icon of Zoom. So you should click just this icon to navigate directly to the session. All parallel sessions are hidden at the moment. So please click here to expand all papers included to the session. You can read titles. You can check who is presenting author. You can read also his biography, clicking on this icon of the person and abstract of the talk. All papers are available in the icon of PDF to read content of full paper. So in order to navigate more efficiently to the system, you can use this green navigation menu on the right side. So we can simply return to navigation menu and for example, find today afternoon session, which is B2. So this is very easy to navigate to find any section. If you want to read whole program, you can click at the top of the table and expand all the program by one clicking. So this is not visible here, but now all papers are visible in the program. Okay, and at your profile, you can still edit. Authors can adjust description of authors' biographies not needed at the moment. Enough good. So hope this menu is enough, clear and intuitive to navigate and to use this conference. So don't hesitate to ask to contact us anytime, to ask our help desk to your support, and hope you will manage this virtual tool in convenient to you way. So at the moment, I would like to invite once more our Vice Rector of the Silesian University of Technology, Professor Tomasz Trawiński, and I would like to give him voice to open our conference in, let's say, formal way. Please, Professor.
Thank you very much, Mariusz. Dear PEMC Council Chairman, dear President-elect of IEEE Industrial Electronics Society, ladies and gentlemen, dear professors, researchers, industry representatives, dear participant of International Conference on Power Electronics and Motion Control. On behalf of Rector of Silesian University of Technology, Professor Grzegorz Benysek, I would like to extend my warm welcome to everyone. I'm proud that so prestigious scientific event became a part of 75-year history of Silesian University of Technology. Allow me to introduce or show some basic details about Silesian University of Technology. The first inauguration of academic year of Silesian University of Technology in Gliwice took place on 29 October 1945. At that time, 2,750 students started their education. The study plans and curricula were based on models taken from Gliwice Polytechnic. Also, the professors of Silesian University of Technology were mainly former employees of Lviv Polytechnics. Today, Lviv belongs to the Ukraine. At that time, there were 4 faculties: chemical, electrical, mechanical, and civil engineering, with almost 200 teaching staff. For the very beginning, the excellent staff of professor was one of the strongest assets of University, Salesian University of Technology in Gliwice. The Salesian University of Technology achieved at the end of 2019 reward in Excellence Initiative Research University Program organized by former Polish Ministry of Science and Higher Education. An international team of experts selected 10 universities, which will receive a subsidy increase by 10% over the period of time 2020 and 2026. The Salesian University of Technology is among of the universities which under the competition will receive the total money nearly 245 million zloty within 7 years. In the competition, applicant university presented the evaluation of its own potential in the form of detailed SWOT analysis, indicators of the publication, design and patent achievements, as well development plans, including objectives and activities concerning mainly the following, like in case of Salesian University of Technology, we focus on increasing the impact of scientific activity of Salesian University of Technology to the development of world science, strengthening research cooperation with internationally renowned research centers, improving the education quality of students and doctoral students through development of modern methods and double diploma programs. Also, we focus on improving human resources policy and finally improving the quality of university management. Our university scientist staff is involved in 12 scientific disciplines: architecture and urban planning, automation control, electronics and electrical engineering, chemical engineering, information and communication technology, biomedical engineering, civil engineering and transport, material engineering, mechanical engineering, environmental engineering, mining and energy, chemical science, earth and related environmental science, management and quality sciences. We decided to focus on 6 priority research areas. We call them POB1, computational oncology and personalized medicine, POB2, artificial intelligence and data processing, POB3, materials of the future, POB4, smart cities and future mobility, POB5, process automation and industry 4.0, POB6, climate and environmental protection, modern energy. Our university is divided, right now is divided into 15 units, including 13 faculties and 2 institutes. We are spread in 4 cities in the Silesia region. The heart of our university, this are still Gliwice, and other cities, Katowice, Zabrze, and Rybnik. We have 2 academic high schools situated in Gliwice and Rybnik. We have over 80,000 students. We are engaged in providing 60 fields of studies. We have more than 180 student scientific associations. We have 21 student organizations active at our university, 13 dormitories in Gliwice, Katowice, and Zabrze. So right now we employ 3,200 people. There are 1,660 academic staff and 1,550 non-academic staff. We have over 150 titular professors, more than 470 doctors of science. We have more than 870 PhD students. The field of research related with power electronics and motion control is present at our university within Faculty of Electrical Engineering since many years. 50 years ago, Professor Bogusław Grzesik intended the creation and became the first head of Department of Power Electronics, Electrical Drives and Robotics. And now, thanks to efforts of the team of this department, we can host PMC event here. Thank you very much for your efforts. I wish you successful conference, fruitful discussions, and new scientific ideas, and establishing new contacts created despite an online conference format. I consider the conference is now open for discussion. Thank you very much.
Thank you. Okay, before I will invite you for the first keynote, I would like to mention our industrial sponsor, as you know, industrial partner. As you know, this exhibition part of the conference was very difficult and finally impossible to organize. So we invited one partner for the conference to have patronage from industry side. So I would like to invite you for a short video of our partner, and if you are interested to listen more, tomorrow afternoon, just before roundtable, we organize short virtual exhibition. You can find it in the conference program. So for those who are interested to listen about our industrial partner, more are invited for this event. So please listen this short video from industrial partner. After that, I would like to invite you directly in the same room, in the same session, for the second hour session, which is keynote address of Professor Johann Kolar.
We live in a world inspired by curiosity. Once you start wondering how things work, the possibilities seem endless. How are these cookies made so perfect and so delicious? How are crayons made in every color in the rainbow? How does a robot learn, and how will that make the world better? Answering these questions with our customers is what we do. At home, at work, or building the next generation workforce. At Rockwell, we're proud to be part of your everyday life and to deliver on what's possible for tomorrow. We make the world more productive, intelligent, and connected. And we don't stop at how. We wonder, what if? What if we could find innovative ways to treat diseases or protect workers far underground or miles out at sea? What if we could feed 10,000 hungry bellies a week? Or millions? Our job is to help industrial companies and their people be more productive and the world more sustainable. At Rockwell Automation, wonder turns what if into what is. And that's expanding human possibility.
So let's start by the first keynote session. Once again, good morning. My name is Pavol Bauer. I'm from Delft University of Technology. My co-chair is Professor Peter Korondi from Budapest University of Technology and Economics. It is my great honor and privilege to introduce the first keynote speaker. Today we have an outstanding keynote speaker and a good friend of the PEMC conference, Professor Johann Kolar from ETH Zurich. Before I read his impressive curriculum vitae, let me stress that Professor Johann Kolar received in 2016 the PEMC Council Award, which is the highest award possible for the PEMC Council. The PEMC Council Award is now renamed to Professor István Nagy Award, and tomorrow, during celebration session of 50 years of PEMC Conference Series, 2 distinguished scientists will obtain this award. Please join. Now back to our keynote speaker. Professor Johann Walter Kolar is a full professor and head of the Power Electronics System Laboratory at ETH Zurich. He has proposed numerous novel conference concepts. Vienna rectifier is very famous, has spearheaded the development of X million RPM motors, has pioneered fully automated multi-objective power electronics design procedures, graduated 75 plus PhD students, published 900 plus journal and conference papers, and 4 book chapters, has filed 200 plus patents. He has received 35 IEEE Transaction and Conference Prize Paper Awards, the William Newell Power Electronics Award, 2 ETH Zurich Golden Hall Awards, excellent in teaching, and also, of course, PEMC Council Award. He is also fellow of the IEEE and was elected to the United States National Academy of Engineering as an international member of 2021. The focus of his research is very broad. Ultra-compact, efficient, wide-bandgap converter systems, neural network-based design procedures, solid-state transformers, ultra-high-speed drives, and bearingless motors. So we have excellent speaker today, Professor Johann Kolar. Floor is yours.
Thank you very much, Paul, for your very kind words. And I would like to thank all organizers of the PEMC conference for the invitation. And it is really my very pleasure to present to you some thoughts on this. You just would please need to let me share the screen if this is possible. It says that I have, oh, now, yes, now it's coming. And I always really enjoyed attending the PEMC conference. My first PEMC conference I had a chance to attend was in 1990 in Budapest. And it was really impressive to me how many very well-known people in my early years of my career I could see they're presenting latest research results. And to me, always the most impressive aspect, besides the high quality of research results, which you could see presented there, was the very warm atmosphere of the PEMC conference. I think this is also an aspect which is really unique to this conference, and for this reason it's really unfortunate that we cannot meet in person, but I will do my best to convey to you certain thoughts on these driving forces of the next step of development of power electronics, which finally will lead us to power electronics 4.0. This 4.0 is a nice coincidence with Industry 4.0, and you will see then along my presentation what I really would see behind this. So let's talk about these X technologies which really can drive us forward, hopefully a factor of 10 of improvement in performance, which those technologies should give us. And I just would like first to acknowledge here a colleague here at my laboratory, a senior researcher, a partner for discussions of any research aspects, and of course a great help with supervising PhD students. Jonas Huber, we had already a tutorial yesterday afternoon. Now, a very brief outline of my talk. You see, we will talk about these X concepts, and X basically means factor of 10, if in any way possible. So it's not really a just incremental improvement, but it should be a massive step forward. You could even call it a moonshot technology. And it finally should lead us to power electronics 4.0, which has maybe certain cognitive functions. It's not just the power converter, the hardware, and the control circuit, which is immediately tied to the converter, but maybe a more general image which we need to have from our converter circuits in future. So this will then be also part of the conclusions here. Just as a very brief introduction, let's go over the different development steps which we could see in power electronics over the years. So if you look at the development, and typically developments of technologies are happening along a so-called S-curve. So you can see that we experienced certain development steps here, starting in 1958 with the introduction of the thyristor, a device which you could turn on but not turn off. It's a semiconductor device at least, and not a mercury arc rectifier, what we had in earlier days. And you could see a certain progress and an improvement in performance. And it's really interesting also to see that already in this very first step of development of solid-state power electronics, already in 1970, you could see the first PEMC conference organized in Budapest. And this is why we can celebrate today the 50th plus anniversary of this conference. So really the oldest conference in power electronics in Europe at least, and this is really very remarkable. Around 1984-85, this is when I started in power electronics, and for this reason I very well remember we had bipolar transistors, which finally then were built into voltage control devices like IGBTs, and there was quite a wealth in circuit topologies, which was invented and coming up and rediscovered to a certain extent, because you had certain topologies already existing in the 1930s built with mercury arc devices. Microelectronics started to play a more and more prominent role. Of course, modulation and control concepts is always associated with certain new topologies. And this gave a really remarkable step in improvement until around 1995, year 2000, once you could see superjunction devices, superjunction MOSFETs introduced, and also first wide bandgap devices, silicon carbide Schottky diodes, and digital power, meaning the digital control of not just drive systems, but also then power supplies, was gaining in importance and is really all around us today. And we are now around the 2015-2020 region here, where we would need to ask what is now the next driving forces, which really would lead us into a fourth step of development, of steep development of power electronics. So again, what are the moonshot technologies? And I would like to share some thoughts I have on this over the next 20 minutes, basically. Not surprising, you would say, wide bandgap semiconductors, of course, silicon carbide, gallium nitride. I mean, what is the reason behind? If you look at the on resistance of a device, of a unipolar device, and this would be the blocking voltage which you would ask from the device, and this is the specific on resistance, so per area of this chip of this device, you would see a quadratically increasing on resistance here over the blocking capability. So this makes devices which are unipolar and built from silicon here more and more less attractive, because you have just high on resistance. You need to do conductivity modulation, which turns your unipolar device into a bipolar device. And then you have certain effects like a tail current, a certain stored charge, and so forth. So if you now would introduce wide bandgap devices which have a significantly larger bandgap, like, for example, silicon carbide or gallium nitride, here shown with this blue characteristic. So then you would find a massively lower on resistance, which basically originates from the higher critical field, which you can allow in your power semiconductor. And the improvement is really nearly 3 decades here. If you would calculate it, you find a roughly factor of 300, at least theoretically, in improvement in on resistance, so the lowering of the on resistance as compared to a silicon device. So this would really give us an exceptional capability, and this is really more than a factor of 10 of improvement, and this is one of the core technologies which will be definitely driving power electronics in future. Also, the switching performance is exceptional. We already mentioned that this is a unipolar device. So you can see this very high switching speed here, a turn-off process of a silicon carbide power MOSFET. And if you compare it with IGBTs here, so this is a pretty slow switching. And we also mentioned already the tail current, and you would have a built-in, you could call it parasitic, but you can make the bug a feature. You have an internal diode of your silicon carbide chip, which is small in footprint, if you compare it to an equally rated IGBT with anti-parallel diodes, where you need to maybe provide the diodes as explicit devices. So this is a key feature of such high voltage, 1200 volts, 1700, 3.3 kilovolts, even 10 kilovolt silicon carbide MOSFETs, which you can find today. But of course, as always in engineering, this comes with certain challenges. So the high IDT, you need to take care on the packaging especially. So you could see this as a bit as a double-edged sword, as it's often called. The advantage is low on resistance, very high switching speed, but maybe certain challenges which are, for example, from packaging. If you now think of a very basic circuit arrangement here, you have your power transistor and you have your commutation loop. And if you would allow a certain switching over voltage, if you turn your device off here, and you just divide the allowed over voltage, which is allowed to occur over your commutation loop inductance here by the dIdt, meaning the current divided by the switching time. So then this allowed voltage translates into allowed parasitic inductance. And if you would calculate it using numbers, you would see that for the nanosecond range of switching time, you would need to have a nanohenry commutation loop inductance. So inductance is lower than this very challenging value. So this is something which is certainly then translating into advanced packaging requirements. Another challenge which is coming with the high switching speed is, and you can see this textbook envelope of a rectangular signal, actually a trapezoidal signal with certain rise times here and a certain repetition frequency. If you switch at 10 kilohertz, you would have this envelope, this spectrum here of your Fourier decomposition. You would have a certain envelope, and this would be the second corner frequency here according to the rise and fall time of your switching signal here. But if you step a factor of 10 higher in frequency and in switching speed, you would find here this second envelope, and which is at significantly higher frequencies, such that EMI is a much more prominent aspect. And also the parasitics of your filter elements, which you might need to provide, are playing much more of a role. So this is the challenges which we need to overcome in order to really beneficially use this device. And one of the options you have, and we will find other options along the way and along our presentation here, is that you, of course, provide kind of a local filtering, and you again could turn, say, the advantage, this potential disadvantage into a feature, make it an advantage if you have your power semiconductors here, and if it's MOSFETs, there is this parasitic capacitance, output capacitance. And you could now, if you need to do in any way, you need to do a certain filtering for attenuating electromagnetic conducted or radiated emissions. So then you could really reduce your inductance such that the current shape looks pretty strange, more or less discontinuous as shown here. The basic idea is if you would have a demagnetization here, you have a certain current in your inductor, and if you have a demagnetization phase, and if the current keeps running in this direction, and you turn on the upper switch, so then you would be hard switching against this diode. So this is something you try to avoid, because even with high switching speed, this would result result in certain switching losses and limit your switching frequency. So why not let the current really go down until it's negative, what you can see better here. So then you would have a negative current which charges this parasitic capacitance and discharges the upper one, such that you can resonate back to DC plus. Then you let the current grow to a positive value, you turn off, you have a current in positive direction, and then you charge this and discharge this capacitance until the diode starts conducting, and you can turn on your power transistor in anti-parallel at 0 volts. So this 0 voltage switching with a very basic circuit without auxiliary circuits built basically into the inverter structure, this is something which is definitely one of the core technologies we need to use. And if you calculate the conduction losses which are originating from this strangely shaped current here, triangular current mode, it's only 33%. So it's not much of a trade-off, you could say, if you have a very low on-resistance device, what we have seen in our first few slides. But the small filter inductor is definitely a way to go if you have this discontinuous conduction mode, you could say, or triangular conduction mode. But maybe you could do better if you go from a 2-level switching, what we have seen now, to a multi-level switching. And why is there so much of a benefit? If you now stack several devices and each device would only need to block a fraction of the total input voltage. So it's not anymore a 2-level, but it's a multi-level structure. In this specific case, it's a flying capacitor multi-level converter. And now you can generate at this switching node different voltage levels here, such that if you would aim for a sinusoidal output, you could really introduce certain intermediate levels. And this, of course, allows to massively shrink your filter inductor here in order to gain in compactness of your converter. So this is something which introduces these extra voltage levels. But if you really analyze the details, this individual switching frequency of an individual device is multiplied to a higher effective output frequency, what is shown in this spectrum down here. If you operate at 2 kilohertz, just as an example of this device, the first harmonic which would be appearing in your output voltage in this waveform here is at 8 kilohertz in this case, because you have 4 devices stacked which are interleaved in switching, and this multiplies the switching frequency. So this means that you are gaining quadratically with the number of devices. On one hand, you are introducing further levels and you are pushing frequency up by a factor of n. So this is a strong scaling law, which we definitely can use to build really compact converter circuits and highly efficient converter circuits. So this is a concept which from the scaling is highly interesting. And it's also especially interesting because we are dividing the blocking capability into a fraction, as we have seen. And if you now check the figure of merit of devices, and this is 1 over on resistance and charge in the parasitic output capacitance, which is related to the energy which is dissipated if you would do hard switching. So then you can see that this performance figure, low on resistance and low parasitic charge here, so this is increasing this figure of merit. So the higher, the better, you could say. And if you check now over blocking capability, you can see that the light blue curve here would be silicon and the dark blue is silicon carbide, and at lower voltages it's gallium nitride. You can see that there is a improvement the lower you go in blocking capability, and there is clearly an improvement of here gallium nitride, for example, or silicon carbide over silicon. So this makes this splitting of the voltage into just a fraction even more attractive. We found this strong scaling law, 1 over n squared, but now we have an additional motivation because the figure of merit of low blocking capability devices is exceptionally better than for high blocking devices. And you can verify this with building hardware, and you can see here a 7-level converter which we built, you can see to be very compact here. You can recognize those filter capacitors. You can also see the small filter inductor. This was a 2.2 kilowatt bridge leg of a 3-phase inverter circuit supplied with 800 volts at the input here. There is no need for forced convection cooling. It's a 99% efficient bridge leg, and you can see here this nice efficiency characteristic, nearly keeping 99% down to 50% of rated load. And if you would build it as a 3-level device, the efficiency would be lower, and 2-level would be even lower. So this shows the compactness. 260 watts a cubic inch is 15 kilowatts per liter. So this is also very high power density if you think that this is natural convection cooling, and it would provide you a 99% efficiency. You can have a second approach, so to say, for those multi-level concepts. You could use the stacked devices as we have seen, but you could build those capacitors to be very small and just used during the voltage transition. So you would keep operating in a 2-level regime, but do have a very well-defined partitioning of your blocking voltage with using this approach here, using those capacitors just to guarantee the partitioning of the blocking voltage. So this is an approach which was proposed by ABB and which is also used in other multi-level converter topologies as an advantage. You can have one of the capacitors built larger, like shown here, and then you can make it a quasi 3-level bridge leg. This is a highly interesting concept which also allows you to spread the heat to many devices and to have a defined blocking stress on the devices. If you go with this flying capacitor structure here and you would aim for a 3-phase circuit like in PV inverter applications, you could confine part of those switches here into a neutral point clamped stage, what lowers the complexity of this and finally gives you, again, an exceptional performance. You can see this nice voltage which you are generating, which is very close to sinusoidal, such that the inductor, the filter inductor, can be very small, and the efficiency which we were able to achieve here is 99.35% at the rated load. So this shows again the capabilities of this approach. And it's just as a final one, you would maybe then say, okay, now this was all at relatively moderate frequencies aiming for the high efficiency. What if we would aim for high power density? And you could use 3-level bridge legs and do the parallel interleaving in addition to series interleaving, and use gallium nitride switches and have a switching frequency per switch of 800 kilohertz. Then gives you a effective switching frequency of 1.6 megahertz, and then times 3 with the interleaving here would let you end up at 4.8 megahertz here. And then you can build here an exceptionally compact converter circuit with integrated filter elements. And this would allow you to achieve a 50 kilowatts per liter power density. So this, I think, underlines that this is definitely one of those X technologies which would drive power electronics 4.0. Another interesting aspect is that you are more and more asked in power electronics to provide wide functionality. So a wide operating range, bidirectional power transfer, all this. And you can, of course, solve such problems with just series connecting or cascading different converter systems. But you would like to maybe do a functional integration and some synergetic association of such converter circuits. So what would that mean? If you supply, for example, a motor drive from a fuel cell, you would find that the voltage significantly drops if you start loading your fuel cell. So you could now place a converter in front which adapts the voltage for your actual inverter stage, which is then driving the motor. But maybe you can do it in a better and a more intelligent way. And this is what I try to show here. You can see a 3-phase inverter structure with LC output filter, which is unavoidable if you use silicon carbide switches here. And you could cut here and insert another bridge leg. which would provide you with, as you can easily see here, a boost functionality. And this is something which keeps basically all the passive elements, but has a higher functionality of those elements. And this is what you can see here. If you now would like to operate in a boost regime, you just clamp the first switch here and you operate only the second bridge leg in order to generate an output voltage here, which is higher than the input. And you can shape this output voltage to be sinusoidal such that you finally can supply a three-phase motor if you would have 3 such modules. If you operate in buck regime, you can see the buck stage is operated and the boost stage is clamped, what means that you have a quasi single stage power or energy conversion. So this is really an advantage of such association, functional integration of concepts. And we try to verify this building here a 3-phase inverter circuit. You can recognize the phase modular structure here. And the voltage which you then generate at the output is very clean sinusoidal voltage, which would be ideal for supplying an electric machine. And this gives you also, again, an exceptional power density because you are using the passive filter elements in a very intelligent way. You can now think further. And this brings us to another X technology. You could say, okay, I built myself such modular, phase modular converter, but would in the next step it be possible to integrate this into one buck bridge leg and have this a bit restructured such that I could also have, instead of 3, just a single inductor here. And if you look at this, and some of you might be familiar with this, this is a current DC link converter, which has a front-end stage here, which just translates the supplying voltage into a supplying current. So you would say, this is nice that I now could integrate and minimize my number of inductive components, but I have this disadvantage of switches which are operating at an AC voltage, and there I need this anti-series connection. But the good news is that there is now gallium nitride components which are AC switches, which have 2 gates, which are fully controllable, but it's monolithic devices. And if you think of this advantage, if you connect 2 devices in series, you are doubling the on resistance. In order to achieve the same resistance then from the individual device, you need to connect 2 more in parallel. So this would require 4 devices. But if you now can confine all this into a single device, so this is this single device which is now available, which features 2 gates, and this is ideally suited. And we tested it also in switching in all 4 quadrants. So it is really operating. It was developed in the Power America project in the US from a main power semiconductor manufacturer. And it's now available in first samples. And if you now use such device, you could build our converter structure with the buck bridge leg here with those monolithic bidirectional switches. And in order to think again of this functional integration or synergetic control, you would not keep your current here constant, but the current would be shaped according to the envelope of your motor currents, which you have here, what you can see in my waveform here, what allows you to keep one of those switches clamped and just switch the 2 other phases, and you find very low voltages in between the phases, which then gives you an exceptionally high efficiency of this approach. So this is really a very interesting concept, and it allows current DC link converter concepts to really enter the stage again. You could say it's not just voltage source inverters in future. And this is what you can clearly see from this slide here, I hope. This is what we discussed, and we had a DC voltage to current translation with the buck bridge leg. But of course, you can have an AC-AC conversion just mirroring here around the DC link. And then you have an AC-AC converter, which basically just employs a single inductive component as compared to voltage source approaches, AC to which is back-to-back connection here of inverter stages, you can see 3 inductors here and 3 inductors on the output side. So this, I think, shows that there is a certain chance that current DC link converters employing monolithic bidirectional switches are driving also the area of variable speed motor drive applications. If you have such switch, you can see that you could also build matrix converters, of course. And why not build an isolated matrix converter, which would generate what is required in telecom, 48 volts here at the output or 400 volts at the output directly from 3-phase. We implemented such concept. It's basically a dual active bridge concept, as you can see here, just with the 3-phase input, a certain selection between the phases here. And if you build it, you would be able to achieve an exceptionally high efficiency, which is very interesting for data center applications, for example, because you have a 24/7 operating time of such converters. So efficiency is really of major importance there. So this was a little bit on converter topologies, multi-level and functional integration, and monolithic bidirectional switches, which will play a role. Now, how about the packaging, which we mentioned already at the beginning? If you look today on building such converter circuit, and you can recognize here this flying capacitor multi-level structure, and you would compare it with a traditional approach. We mentioned the advantages, which are clear from efficiency. Power density is high, but still you can do better if you build this conventional 2-level approach. In a highly compact form, you might be able to do better, equal in efficiency, as you can see here, but even a little bit higher in power density with the conventional approach. So this is kind of coming to an end. We will not have PCB-based converter circuits with very high performance or top-notch performance, you could say, but you need to follow an approach which is already existing in industry, which ties then this PCB-based converter into a kind of more, still of course inhomogeneous, but kind of a monolithic, kind of an integrated circuit in power electronics. I think this is a clear next step in development which we will recognize. And the issue is how to do this at the university. You need to have a technological partnership with industry. Otherwise, you are kicked out of this really highest performance converter designs and realization. In this case, goes even a step further. And we mentioned already this to be kind of monolithic, but for example, a semiconductor manufacturer from Japan here built a matrix converter from gallium nitride devices, those AC switches, which we have seen just in a single package here, and even with a highly integrated gate drive, which is called drive-by-microwave technology. So this, if we want to be competitive on a university level in such technology arena, so this is really a challenge I would clearly see. But it is necessary to really enable this fourth step of development in power electronics. And just let me come more towards the end of my presentation here to the fifth key technology I would see. And it's clear that digitalization plays a role in design, but also in the operation of our power converters. I mean, we could recognize a breathtaking development in computational power over the years. So this was shrinking feature size, Moore's law, I think all very familiar to you. And still this is further improving, not maybe with smaller feature size, but with parallel operation of several cores. And we just can see that there is a relative cost reduction for a given computational power, and the computational power is, as mentioned, increasing, which allows us to use this for the design of a circuit, but also in the operation of a circuit. And I think this is what you might have seen from an earlier presentation I did at certain conference. the design space mapped into a certain performance. This is the whole goal of engineering. And we would, of course, like to find the limit of performance, the best performance we can achieve. And if we have a certain improvement in technology, we might be able to shift this limit. So this is a certain understanding we can gain. And it's always not just efficiency or power density, but it is multiple performances which we should satisfy at the same time. So this is one aspect. But once you really have this full model and a fully automated design, so then you can also trace back. We mentioned this optimization, but we can also understand, and we select values here which are very similar in performance, but very different concerning the sets of parameters which are used. This is something you would not think really to be true if you would not analyze in detail, but actually if you analyze this for even a single transformer, and you can see this transformer here, and you can see different parameters which you could find: current density, peak flux density, increase in temperature, and so forth. And you would have this Pareto front here, what we have seen conceptually on the last slide, and you would select for a certain performance here, which would be this final performance point. And you can see that your all different kind of designs are resulting in the same performance. So this is something which is not very well researched at the moment, but this is highly important, I think, in order to maybe also satisfy certain cost targets besides efficiency and power density and so forth. So this is really a very interesting research topic also. And if you now think of the next steps in design, you would say, okay, state of the art, we have certain models now and we simulate and we can do this multi-objective optimization. In the next step, you might want to have an assisted designs, a certain support, and you would have a bit an abstracted database of earlier or former designs. And then in the next step, you could think of that your design, automated design system also suggests already certain designs. And at the ultimate step, you would think of an autonomous design where you could independently generate a full design and you would just as an expert judge it at the very end. So this is something which is interesting and which is definitely also one of the research directions and the key enablers for progress in power electronics. And part of this is this digital twin concept. I have not too much time to discuss on this, but if you have a simulation model, and if you want to find a very fancy name for it, call it the digital twin. Basically, it is mirroring your physical asset here, and you can then feed in operation data back into the model in order to find out the stress in your system based on the model, and you could do predictive maintenance, for example, as one of the applications here. And this more now guides us to a general, more general understanding and application also of power electronics converters. I think in the past you thought of a core function which you needed to implement in order to drive an electric motor. But in future, you could say, okay, this is really a core of intelligence which I have with my converter circuit. So why not to do a certain actuation, a certain stimulation of my load or even of my source in order to identify my environment and to find out certain parameters which would allow me to adjust certain control parameters or to find out if this system is really operating as desired. So this can be spread to further and further layers. And you can see this here. This was taken from Siemens from a presentation at the ECPE workshop. You can see this is what we, I think, thought about today and they are thinking mainly about today, but you could have certain intelligence already built locally at the chip level in order to identify certain stresses or certain wear out mechanisms like a bond wire liftoff or delamination of your chip. You could communicate to a next higher level here. You could bring in certain sensor data from your load, and this then could be communicated to a higher and higher level, and even could give you a certain understanding of the situation in the whole fleet of devices which are underway. So the converter, I think, needs to be seen with its interface, communication interface to the environment and finally into the cloud. And there is, of course, all different kind of concepts you can apply, like machine learning, artificial intelligence, all those fancy words which you can see, they will play a certain role in this context here. So what is the conclusions? Very simple, basically. You can see we have a set of driving technologies here. And I also added multi-level multi-layer ceramic capacitors and high-frequency magnetic materials. We did not discuss on this, but they might play a certain role here. Besides, of course, wide bandgap semiconductors and digitalization, which are the key technologies. Multi-cell, multi-level gaining definitely in importance. Functional integration, as we have seen, giving us advantages in 3D packaging and integration, being one of the really core technologies also. It's not sufficient to have only the chip. We need the right package in order to interface it to an application. And this is how you could see things. I think in this more middle power range with large number of applications, we will see kind of integrated circuits, power converters translated into kind of integrated circuits, medium voltage gaining in importance in high power EV charging, in hyperscale data centers. There is plenty of room at the top with silicon carbide components, but there's also plenty of room at the bottom. You maybe remember from Richard Feynman, once he kind of invented nanotechnology, he mentioned that there is plenty of room at the bottom. So power supplies on chip, very low power electronics will play a role. And our converter will not be sufficient. It will be the system which will be important, either the connection in the power, considering the power transfer, or the exchange of information. And cost is the driver in industry, but luckily we are at the university and can think a bit in a more general context. So this brings me to the end of my presentation, and I really would like to congratulate the organizers and the whole PEMC conference series for the 50th anniversary. And it was my very pleasure and my very honor to present this keynote to you today. And hopefully I could give you a little bit a glimpse of what I would see as driving forces for the future development of power electronics, which will be very dynamic. Thank you.
Yes, thank you, Johann, for a very inspiring talk. Thank you for congratulations for 50 years anniversary. Tomorrow we have a special session where we will also hear about the history and about the future of the PMC. Please join. I have a few questions from the audience. I know we are over time. The first question is from Hamed Mashinki from Japan, I guess. Thank you for excellent presentation. What is your prediction about the future of semiconductor switches, especially the role of gallium nitride in devices?
Yeah, I think we already achieved a very high performance of gallium nitride devices. There are certain issues like the dynamic resistance. This is still, I guess, an issue to be solved. And to me, it seems that the devices already reached a level of performance, which unfortunately, due to the poor packaging, is not really available for the general application. And I think this would be an aspect which I really want to highlight. Besides, I mean, people are working on diamond devices. People are also working on very special other type of devices, which is not semiconductor devices, but more like a vacuum tube. So if you consult literature, there is all different kind of interesting device concepts coming up. But I think the device itself, or the semiconductor material itself, and the structure of the device, I think is a very interesting aspect. But the packaging, in order to make it available, maybe integrate the gate drive in order to ease the usability of this device. I mean, this commutation loop discussion, vertical or horizontal commutation loop, I think this is what we had already 40 years ago, or 35 years ago, at least as far as I can recognize. And this needs to be solved in order to make the device features and high performance available in an application. And this is a key aspect which unfortunately is largely missing today.
Yes, and the second question is from Ding Xiao Lu from TU Delft. Thanks for the presentation. Regarding the second point of the presentation, I understood from the argument that power efficiency and density can be improved by the idea of multi-level and modularity. But how do you consider the stability issue of the whole system as much more components are added?
Yes, I think this is a very interesting comment and a very reasonable question. I think on one hand, and there you can see with the multi-level, maybe if I have just two pieces of answer here. The one is you have this digital signal processing capability, which now allows you to really manage the complexity of such multi-level converter structure. I think this is something which is what was basically not really possible before, especially if you aim for very high switching frequencies. So digitalization also plays a role together with multi-level topologies. I think this other aspect, of course, that the larger number of devices, the larger number of gate drives, a certain fit rate, which you might see for the switch and the gate drive, which would then finally maybe not allow you to achieve an exceptional high reliability, maybe high efficiency power density, as pointed out in the question. I think this is something which still needs to be analyzed in detail. It's very difficult at the university level to really find an answer which is based on practical experience. You can calculate, you can see, of course, if reliability decreasing, you would maybe want to use topologies which provide a certain redundancy, what you can find from modular multi-level converters, not from the flying capacitor converter. And I would see this as, from the flying capacitor approach, which I presented, as one of the downsides of this topology. But on the other hand, if you now would be very optimistic and you would say, okay, how many transistors would we build into an integrated circuit today? And now if I think of having the gate drive and the switch implemented into a single device, which is manufactured in a kind of clean room environment, so then maybe you can reduce these potential failures which you find if you would populate individually a large number of components. So this could be reduced to an extent where you really could achieve a reasonable performance also concerning reliability. But it is a very true question, and basically you would aim for redundancy, which not always is the case. And this is something which needs to be identified in future, but companies are hardly sharing data on certain field issues they might find with their converters. So for this reason, this is a kind of challenging university topic, because you would not have really a closed loop in the sense that you can do experimental verification, because the data from the experiment in the market is not available to you. It's just considered secret from the companies.
Okay, I know we are over time, but I still tend to ask some very brief questions. If you can try to...
I will do a brief answer.
Okay, so there is a trade-off between going to the higher and higher voltages with blocking capability devices versus multi-level concepts. And this is a question from Dana Shri from TU Delft. What is the view about the medium voltage silicon carbide MOSFETs? Now you have a 6.5 kilovolt or 10 kilovolt over 1.2 kilovolt MOSFETs. So what's the trade-off, higher voltages or multi-level concepts?
Very good question. Just let me answer based on what we did in solid-state transformers. We built the multi-cell topologies, which were using devices of lower blocking capability, like 1.7 kilovolt devices, and you needed to stack several of such units on top of each other. And then we built one with a 10 kilovolt silicon carbide switch. And it's a single stage circuit, very conventional, 2-level bridge leg. You can do soft switching like what we discussed. And this is so low complexity that I think even if you think of all those advantages which you find from multi-level topologies, this is a striking advantage if you can build a very low complexity single stage converter with a 10 kilovolt silicon carbide MOSFET. So I would really see a very interesting and kind of bright future of those medium voltage devices, because yeah.
Thank you. That's a clear answer, I think. What do you think about the EMC problems generated by the increased number of high-switching devices? Question from Peter Korondi, my co-chair.
Yeah, I think you need to solve the EMI issue at the very source. I mean, there needs to, you should aim for building bridge legs with certain kind of integrated filtering already, and not I mean, this switching node, which is changing its voltage with 100 kilovolts per microsecond easily, or even 500 kilovolts a microsecond, what we could see from gallium nitride. I mean, you need to tie a filter inductor in a certain way and filter capacitor such that you can really have a continuous output voltage generated. If you are doing a PFC rectifier, for example, this would be naturally necessary and the case. So you need to carefully think about this. You need to introduce certain shielding layers. Maybe if you build a transformer, it's not just the primary, secondary winding, but also the shielding layers. This will be at least in certain lower power applications up to several kilowatts possible with PCB-based windings, such that you can introduce shielding layers. But yes, this is definitely far more challenging than before, and you would need to use advanced techniques. I'm very general here, I'm sorry, in order to handle this, but I think it can be definitely done. And if you look at automotive applications, for example, I mean, they are using gallium nitride or silicon carbide in their future systems, definitely. And the PCB-based windings of inductive components also provide you certain means for shielding, but this needs to be all thought at the same time. It's not designing the converter afterward thinking of the EMI, but this just goes together in one step.
So multi-objective optimization from the very beginning, let's say, let's put it this way. But here I had a question for myself. Where do you see the role of artificial intelligence in the optimization process? How do you see that? It's a big topic, I know. Please.
Yeah, I think it's running as any new technology. It's running through a certain hype. I mean, it's a buzzword which you can find nearly everywhere now, and the role really, I think, is not so clearly visible, and even that you would for sure know that this is the role of artificial intelligence. I think if you have very time-consuming processes like finite element simulations, and this is what we did for optimizing inductors, for example. So then you could think of training, and you have certain operating requirements, and you have these finite element field simulations, which then generate you certain loss figures of your winding, for example. So this is what you could train your neural network, for example, to learn for certain operating conditions and certain geometries of your magnetic device to really learn this, do this training offline, which is very time consuming, and then use this as part of your design. I think this would be something which is really beneficial, and what we found to be beneficial. This would be in the design process. I think in the operation, of course, you can then have certain sensors and then interconnect this information into a neural network. I think the training of this network, if you aim to identify failures, you would need to figure out in advance enough training situations for your network that you can really be sure that this works in a satisfactory way finally in your application. This is one of the challenges, and it's black box. What to me as an engineer is a bit hard to accept, and if you would implement it for guaranteeing safety features and you are only 95% sure that it works, this missing 5% might really be a challenge to convince a lawyer, for example, who then...
Okay, I can imagine. I have many more questions, but I promise now very last question about autonomous design optimization, which is dependent on the availability of the reliable models. What are the constraints and limits what you see? Question from Zdeněk Peroutka.
Yeah, I think the models which we have available today, which are also including high frequency effects, if you talk about magnetics, which are partly difficult or considered difficult, I think we have pretty comprehensive models already. It is really just implementing this optimization procedure, which is not too difficult, and it really provides you a very good insight into your whole design process. And as I tried to highlight, not just for the optimization direction, but also then tracing back from which regions of your design space the different very closely neighboring points would originate from. And I think this is something which is kind of opening another dimension in understanding as compared to what we did before. Luckily, all those optima are pretty flat, such that with a good engineering understanding, you can arrive at very good performance. You would not necessarily need to do it, but once you have it installed, I think as an engineer, this is really fascinating what insight you can gain.
Okay, thank you, Johann, for your very inspiring talk. Thank you for your answering of your questions. I'd like to give you a virtual hand with all the applause with all the participants of the conference.
I very much hope to see all of you in person at the next PEMC conference. I very much hope.
Thank you very much again. And sorry, General Chair Mariusz Stępień, that we took it over the time, but I think it was a discussion which couldn't be stopped.
Okay, thank you, Mariusz. Thank you very much.
Thank you, Johann, for this nice talk. Thank you.
Thank you.
So let's continue with next session, which is a bit delayed, but hope we'll manage this time. So now I would like to invite co-chairs for this session for Students and Young Professionals Activities. And I would like to invite Marek Jasiński, who is chair of Industrial Electronics Society Committee for Young Professionals, Students and Young Professionals, and Professor Mariusz Malinowski, who is president-elect of Industrial Electronics Society, to co-chair this session. So hope you are present here.
Yes, good.
I would like to give voice to Marek Jasiński to coordinate this session.
Yes, good morning to everyone. Good afternoon, good evening. Thank you very much for your kind introduction. I'm trying to share my screen. Do you see my screen now?
Yes, your screen is seen.
I think this is not mine screen. This is the...
This is the presentation, not the screen.
Yes, just a second. Okay, you shall see my screen now. Hello.
Yes, we can see some background.
Sorry. Again.
Marek, we can show this presentation if you want to show it.
Okay, just a second. Once again, I will try some technical issue probably with my computer. Now you shall see my screen.
No.
Please
Okay,
stop,
so
please stop share screen and share again, okay?
Okay. So maybe if you have my presentation, you would share the presentation. Stop share. Okay. And now.
So.
Okay, I see the presentation. So my name is Marek Jasiński. I would like to welcome all of you to the Student and Young Professional Activity at PEMC conference. Next slide, please. So thanks to Mariusz and another chairman of this conference, we would have opportunity to interact with our sponsor. Next slide, please. So I would like to present during this short introduction the idea of keynotes under the tutorial and industry links, and then some invitation to industrial electronics. Next slide, please. So this is our schedule for today. But about this, Pavol Lasek will tell more after the presentation. Next slide, please. So, and now I would like to welcome President-elect Mariusz Malinowski. Mariusz is a President-elect of Industrial Electronics Society, and he is very open for student and young professional. He always supporting our events. So if we have Mariusz with us, please, Mariusz.
Yes, I am already here. Thank you very much, Marek, for the kind invitation and introduction. On behalf of the Industrial Electronics Society, I would like to tell that students are very important group of the members for our society. I was in the past the chair of the student activity, so I know how much effort the Industrial Electronics Society put for the students. Currently, this support is much more extended. For example, to support for the student branches. So the student branches can be created in any of the university and can ask for support from Industrial Electronics Society. Also, we have a program supporting the students from different countries to visit the conferences. Of course, it's more valuable during the after pandemic time, but our program is running since 2000 as far as I remember. So this is a proof that Industrial Electronics Society pay a lot of attention for the students. Also, this is I think a very interesting activity that Industrial Electronics Society also organize some of the special workshop tutorials and invite also distinguished speakers, especially who prepared the speech, the lecture for the students. And we'll have a such also example today because we invite Professor Benysek to give a dedicated speech for the students. So we are proud of this. Also, during the regular conferences, as well as we try to do this also during the virtual one, the student forum, which is also the platform for the student to make some of discussion, to exchange the ideas and so on. And if the students are already the IEEE members, we can provide some of the complementary Industrial Electronics Society membership. So please take this opportunity to join us. Also, some of the options, some of the possibility for the young professionals and students, it's interaction between the professionals. You can see how many distinguished professors are already participating in this session. So you have a chance to make a close contact with them, maybe to exchange the ideas, to make some consultation and so on. And also, thanks to our society, you can elevate your link to the industry and link to another professionals from the same society. So thank you very much for joining for this session. As I told, this is very important part of the activity of our society. Thank you very much.
Thank you very much, Mariusz. And I would like to stress that this event would not be possible without a great effort of Mariusz Stępień and Paweł Lasek, because they are doing a great job. Next slide, please. So for today, we have a presentation from Professor Grzegorz Benysek, Ekoenergetyka Polska. This is a presentation about new trends in green transportation. Please let me introduce Professor Grzegorz Benysek. He is a great professor, a great scientist. However, he is joining also businessman profile. His scientific research focus mainly on issues related to the use of power electronic system, EMC compatibility. He is an author of over 100 scientific papers and several books published by the Springer London. Also, it has been printed in China. He cooperates with industry, not only in Poland, however, also in Europe, in Asia. And his focus is on the highly efficient electrical communication and infrastructure of the transportation. Professor Benysek, are you with us?
Yes, I am here. Thank you for your introduction.
You have the floor. Thank you very much.
Ladies and gentlemen, this is my pleasure to be here with you, and I would like to thank you to organizers for the privilege to be here with you. And I would like to tell a few words about the new trends in green transportations. If we will take a closer look on the elements of the electrical cars, trucks, even planes, the most crucial element of every vehicle, there is the battery. And of course, there are so many different types of batteries, but we should be keen on two major elements. I mean the size of the battery, because of the size of the battery determines the range you can achieve. As you know already, at this very moment, some of the cars we are able to reach more than 700 kilometers on one charging. So the size of the battery, this is the one of the major issues, but also we should be very keen on the power density, because the power density determines the charging time. And even now, from a few of the producers, we can see that they are claiming that the charging currents are at the level of 3 or even 4 C without the influence on the lifetime of the battery. But at this very moment, talking about the energy density, we can see that the most important element, which determines also the range, is at the level of 260, 250 watt-hour from the kilogram. but in the next 2 years, some of the producers are claiming that this parameter will go up to 450 watt-hour from the kilogram. So that means that in the next 2 years, our electrical car will have a range above 1,000 kilometers, and there will be no problem to achieve this range. Maybe take a look at few electrical cars which are already on the market. Here, this is the Renault Zoe. This is the bestseller electrical cars across Europe. More than 40,000 new cars were sold already. And you can see the battery size. We should be very keen on the user-able size of the battery, because this determines the range of the car. Of course, with this car, we are also able to recharge the batteries with AC as well as a DC socket. And what we should be very keen on is the charging time, not the charging power. Why we should not be very interested in the charging power, I will try to explain you a little bit later. But you can see that from 5 to 80% state of charge, you are able to recharge your battery in about 45 minutes. Of course, if you're using the CCS2 socket. Another one, great car. The parameters of this car are quite expressive, and the battery is not so because the size is above the 80 kilowatt-hour. But at this very moment, this car has the largest charging power, 270 kilowatt. And because of this power, we are able to recharge the car from 5 to 80% state of charge in less than 22 minutes. So with this car, this is almost very, very easy to drive across Europe, across Poland. Of course, if there is the fast charging infrastructure, and this infrastructure is easy to use. And the last model I want to share with you, this is the model Tesla Plaid Plus, which will be on the market at the end of this year. The producer is claiming that the maximum power will be above 1,100 horsepower. And of course, you can recharge this car with DC only, with DC socket. And the size of the battery is at the level of 120, 130 kilowatt-hour. These numbers are already, they are not precise information about this size. But I can tell you that about 7 years ago, the size of the battery at the level of 130 kilowatt-hour was able to implement in electrical buses. You can see how the energy density is going up. That's the same batteries. After 7 years, we are able to implement in normal vehicle cars. But why shouldn't we be very keen on the numbers? Because here you can see the charging characteristic for the Porsche Taycan Turbo S. And you can see that depending on the state of charge, the charging power is variable. The maximum power, 270 kilowatt, is possible to get only for about 4 or 5 minutes. After this time, the charging power is going down to 200 kilowatt, 150 kilowatt, and lower. This is related to the efficiency of the cooling system of the battery. So, in my opinion, you should not be very keen on the charging power, because as you can see here, the charging power is possible to get only for 5 or 4 minutes. But you should be very keen on the charging time. You should ask to the sellers, what is the charging time of your car you are trying to buy? And also, what is the usable energy of your battery in your car? The same story is with Tesla. You can see that the maximum power, charging power, is possible to get only for 1 or 2 minutes. After this time, depending on the state of charge, the charging power is going down considerably. So this is another issue. Where from comes this problem? The major problem comes from the battery. because if you are trying to recharge your battery with such large of current, there are some temperature issues, there are problems with the cooling system, and that's the reason why the BMS of the batteries is limiting the charging power of your car. And of course, the electrical cars producers are very, very proud of the power, of the horsepower of the electrical cars and the acceleration. For example, here you can see for the Turbo S on Plet Plus, the kilowatt. But as we know, this power is only possible to get only for 2, 5 seconds, 10 seconds, dependent on the power level. Again, this is related to the battery. So in my opinion, the electrical cars, also the trucks, this is the battery, nothing else. The battery, which is the most expensive element of our vehicles, and we should be very keen on this element. Let's talk about the charging infrastructure. How should look like the infrastructure across Europe? If we will take a closer look at drivers, European drivers profile, you can see that more than 87% of the European drivers, the daily mileage is below 60 kilometers. So according to the WLTP standard, you can see that the daily energy consumption is at the level of 1580 kilowatt hour per day. So if you have access to even one phase socket with 16 amperes, you have no problem to recharge your car during the 4 hours of the night tariff. In Poland, the night tariff, the prices of the energy during the night tariff are very, very, very low at the level of 27 groszy. 0.27 zloty. So that means that's the daily cost of using your electrical car. If you are using your own socket, is below €1. Of course, everyone can ask me a question, how many people are living in single-family houses? So across Europe, more than 50% of the people lives in single-family houses with access to the one-phase socket. Of course, if we are not so lucky to live in single-family houses, how we are able to recharge our cars? So we should recharge our cars if the infrastructure, the wall boxes, small and slow chargers will be at the parking lots, in the places where we are living, where we are working, because during the 8 hours or 10 hours which we are spending in home or in work, there's no problem to recharge a car. But of course, there's the question how to recharge your car during the long trips for the taxi drivers, or as I call them, the active drivers. So the infrastructure should be hybrid one, where there is the place for the wall boxes with small charging power, about the 11 kilowatt, 22 kilowatt, 7.5 kilowatt, even lower. But there is also the place for fast and ultra fast chargers. At this very moment, we have the newest standard, Shademo 3, where you are able to recharge your car with power above 1 megawatt. That gives you an idea in which direction this element is going. And where should we recharge fast our electrical cars? On the gas station. For example, like it is in Poland already, the Orlen implements across the highways the charging infrastructure, the fast charging infrastructure, where you are able to recharge your car in 2025, depends on the parameters of your car, your battery. And of course, in Poland, more often you are able to see something like this. We call it the charging hubs. This is the place dedicated only for the electrical cars, and during the process of charging your car, you are able to eat something, you are able to check your emails, you are able to work, you are able to relax, you are able to watch TV. You can do whatever you want during the 25, 22 minutes during the charging time, and you are able to go further. And of course, we can ask you a question, what next? If the battery vehicles are almost around the corner, what will be in the future? In my opinion, the future which will be in parallel with the battery vehicles, there is the hydrogen. The hydrogen, from the production of the green hydrogen up to the long-term, long distance transportation, the short distance transportation to the distribution. And even now at the market, there is more than 20 different type of trucks which are based on the hydrogen, not only from Daimler, not only from Hyundai, but also Renault, Toyota, and other producers are already in they offer the trucks with the hydrogen. And also there's at least a few lines where the hydrogen rails are operational already. In Germany, there is about the 3 lines where we can see the hydrogen trains. And also the Airbus is claiming that in about the 2025, there will be the first hydrogen plane, which will be operational. And we are not able to forget about the drones. I call this the 3D transport, because in next 3 years, there will be the first commercial ready drones, which allows you to transport to the people. For example, in Dubai, the first commercial available system will be ready even this year. But in my opinion, in next 15-20 years, our future will look like that we will travel with our own private drones to our universities. We will travel, go for shopping, and our cities will look like here in Fifth Element. So in my opinion, in 20-25 years, the future will look like here on this picture. And of course, the last one thing I want to talk about is the carbon footprint. Are the electrical cars responsible for the footprint? They are producing the CO2? Yes, they are. In Poland, we are producing a lot of green energy. We are able to recharge more than 2.5 million electrical cars only with the green energy. But still, during production of the electrical cars, during the utilization, we are producing the CO2. There is no question about this. But which of our behavior is not producing the electricity? When we are buying the telephones, smartphones, new TV sets, we are producing the CO2. When we are buying a new pair of jeans, we are producing a lot of CO2. I'm very often asking a question, why we have every year, every 2 years to have one new smartphone? Our old smartphones are not operational. They are operational. So there is no need to buy every 1 or 2 years new smartphone. There is no need to buy a new TV set because there is the 4K or 8K. All these activities are leading to production of the CO2. There is no question about this. And what is happening with all these smartphones, laptops, and TV sets? Even now, despite of the regulation, most of this equipment is going to Africa. You can see some pictures how this equipment, our equipment, very often our equipment is utilized. You can see here on this picture only the children. Why the children? Because the average lifetime there is about 37 years old. On this picture is the guy who is 27 years old. So you can see he has only the 10 years life left. And in my opinion, we should think about this, of course, how to limit this, how to try to convince to the people to behave more environment friendly. Thank you for your attention.
Thank you very much for a very interesting presentation. Now the discussion is open.
I hope so. I was on time.
Yes, definitely. We are on time. Is there any question? So if I couldn't see, let me start the discussion. I wonder, because I saw in your presentation the charger from Ekoenergetyka. This is the company that you are very familiar with. And what is the price and what is the nominal power of this charging station?
Oh, I cannot tell you about the price of the charger because it depends. It depends all the time on the project we are realizing. But I can tell you a few words about the power. The maximum power of the chargers for the electrical cars, vehicle, not the buses, for the vehicle, there is, for one socket, there's the 500 kilowatt. But at this very moment, if you are taking about the size of the battery, the biggest size of the battery is about 108 kilowatt hour. So you are able to charge your car, your battery, with a current at the level of 3C or even 4C. But as you've seen this, talking about Porsche, this power you are able to charge your car only for a few minutes. So we are able to build 1 megawatt chargers. This is no problem at all for us. But the battery technology of the battery limits this power to the level of maybe 2-3C. So the power of 200 kilowatt, 250 kilowatt. But the new standard is the 350 kilowatt per socket. In comparison to the buses, we are able to recharge our buses with power at the level of 1.2 megawatt already. We were able to win a tender in Hamburg and also in Monachium, München, where the chargers are with power at the level of 1.2 megawatt.
Mm-hmm. I'm impressed. There is one question from Indrek Rosto. Indrek, are you with us? So I can read the
yes, I am.
So you can provide this question by yourself.
So my question is regarding new trend which I have read about, new mobile electric vehicle chargers, where there is no grid connection, or there is the grid cannot support fast charging, whatever. Then there is a trend to build mobile chargers. Do you have such products already in development, and what will be the future? Is it a trend?
You know, mostly we are producing these elements on which there is the market ready. Of course, we have in our product line not only the fast charger or ultra fast chargers or chargers for the electrical buses. We have also here the wall boxes, DC wall boxes, only DC wall boxes, because I think so that in the future there will be no onboard chargers in electrical cars because of the size, because of the weight. There will be only the DC possibility to recharge with DC current. But also in our offer, we have the wireless chargers, but there is the minor element of the market at this very moment. But if the market will be ready for this kind of solutions, of course we will offer this.
Okay, thank you. What about the hydrogen in Poland? Did you consider this opportunity? As far as I know, this is a great challenge in US now, also in Austria.
Yeah.
So maybe in Poland, it is also a good idea to introduce this type of vehicles.
Yeah, sure, for sure. in my company, we will have our product, the first refueling hydrogen station in next 2 years. In next 2 years, we will have, because as I said before, in my opinion, the electrical cars will be two kinds. One kind where the energy storage will be in the form of the batteries. The second one where the energy storage will be in the form of the hydrogen. So that's the reason why I'm very keen on this technology. Of course, in Poland, still we don't have almost no industry related to the hydrogen, because we don't have our Polish producer of the fuel cells, electrolyzers, etc., etc. So there is a great gap which we will have to fulfill, but I believe so that we have to try to accelerate our works in this subject, because there is no question about this, that the hydrogen, especially when we are talking about the trucks, will be the major element.
Okay, thank you very much for this answer. And maybe the last question from Peter Korondi. Peter? Okay.
I can tell you. So you mentioned the wireless charging, and I just wondering whether we can apply it for a moving car, for example, in a special highway, or maybe when you stop at the red light or something like that.
Yeah, maybe it will. There will be one of the possible solutions, and there is no technical issue that we cannot implement this kind of solutions. There is no question about this. There will be very different types of the recharger of your cars in your homes, at the gas stations, during the red light, etc., etc. Maybe during when you are moving, when you are driving. But at this very moment, there are the most important chargers which are on the market, the socket chargers.
Okay, thank you very much. And Bauer, Professor Bauer.
I have several questions. The first question is, I liked the part of the personal air mobility, that you are foreseeing the air mobility as the future of the transport. So what is exactly the improvement of the battery weight to reach this battery energy density to reach this point? Did you calculate it?
Could you please repeat your question, please?
We need to have a battery with a very high energy density,
yeah,
and power density, of course, with very low weight.
Yeah.
So what is the numbers to reach the point that we are able to say that personal air mobility will be realistic?
Yeah. So at this very moment, most of the producing are claiming that they have the energy density as the level of 260 watt-hour per kilogram. So that gives you an idea that you are able to reach 1 kilometer or more from 1 kilogram of your battery. But in 2022, some of the producers are claiming that they will implement the batteries with the energy density at the level of 450 watt-hour from the kilogram. So there will be double these numbers. And of course, we have also the batteries. For example, when we are talking about the Porsche Taycan, where there's the possibility to recharge your battery with current at the level of 2.7. So in my opinion, as well as with energy density is going up, the power density will going up also. And also the power of the drive will go up. But where is the limit? I don't know. I can tell you that in the power system already, I'm implementing the NMC batteries with the C coefficient at the level of 10C. But already in the electrical vehicles, this kind of batteries are not implemented because of the costs.
But energy and power is two different things, and it's difficult to achieve at the same time both. But I was asking about air mobility, about the personal air mobility.
Air mobility.
In our calculations, you need to go to go up with the energy density about 10 times to be realistically really thinking about this. So I was curious about this number. Next question, our comment, we are developing chargers directly from the photovoltaics, not with grid connected, but photovoltaics, especially on the parking lots and parking garages where you have a lot of space for photovoltaics. This is a real green solution. I didn't hear anything from you about it. So how do you look at it?
But you know, talking in real life, how much power you are able to implement in the parking lot? 100 kilowatt PVs, I don't know. And one car, if you have to recharge one car with about the 85 kilowatt hour, so you can see that you have implemented not only the PVs, but only the batteries to store your energy. From the economical point of view, this is not a very good solution. In which direction we are going? In Polish, we have the law where you are able to sign the PPT agreement, so you are able to produce the energy, the green energy, in any part of Poland. And this energy, from the law point of view, is considered as you are charging with this energy your cars. So there is no need to be the PV installation just in front of your chargers. You are able to implement the PV installation in any part of Poland, and still, according to the Polish law, you are able to treat this as the green energy, which is sold from your chargers.
I disagree with you, because then the grid will be overloaded with the peak power, and this is what is bottleneck at this moment for the further expansion. Yeah. So what you need is to have it local solutions, local charging, local production of energy, and not to overload the grid, not to place it anywhere in Poland and then transport energy over the half of the country. The last question I have is what do you have?
This is not so easy answer, sir, because much more easy and much more economic efficient solution is to implement in front of your charger the small, extremely small battery. And in this way, you are able to lower the maximum power which is taken from the load, from the power station, from the power system.
I don't want to go to discussion. We made the calculations that if you implement 1 million cars in the Netherlands, you have to make your grid heavier, maybe 3 times in some places, which is completely uneconomic. So local charging is okay.
I know this. So that's the reason. That's the reason why I said that we should recharge our cars during the night from our wall boxes. When the curve of the power curve in the power system is going low. So you are improving in this way the efficiency.
Gentlemen.
Can I suggest move this discussion to lobby or breakout room? So this is to continue. So this is
I see that
for such discussions, but now we should follow, because we start sessions very, very soon. So this is.
Thank you very much for excellent hot discussion. And now I would like to thank you very much for everyone. And maybe I would like to introduce Pavol Lasek. Pavol, are you with us? Yes, Pavol is with us. He is a general chair at Student and Young Professionals Activity at PEMC conference. So you have a floor, Pavol.
Okay, thank you. I will set on behalf of PEMC to cooperate the competition for students and young professionals, as well as communication to the participants. We are currently having a competition going on. The students were grouped into different teams, and they are preparing a video. The theme for the video is how would you encourage and inspire young people to progress towards studying industrial electronics and related subjects. And currently there are two groups, two main groups, let's say. One group are the graduate students, which were divided into 4 teams. These students are also the participants of the conference. And the second group consists of invited undergraduate students from a couple of universities. And the competitional final will take place at Wednesday during the Students and Young Professionals session around noon. So stay tuned. We will be having an open voting. So every participant of this conference will be a judge of what they've prepared. And that's it. Thank you.
Thank you very much. All of you are welcome, and please remember, not only student and young professional, but also their mentors are very welcome. So please.
Maybe we should add, Marek, that not only Professor Benysek took this keynote. Every day we have one students and young professional keynote. Tomorrow is Dr. Piotr Zimoch afternoon, and last day, just before this final of competition, is Professor Anton Rasolkin from Estonia will give also students and young professional talk.
Thank you very much, Professor Mariusz, for this information. And if you have any other questions, please send us your email or try to catch us in the lobby. Thank you very much, and the session is closed. Very sorry for the delay.
And we invite everybody to join parallel sessions in proper rooms. So thank you for attention here. Thank you very much.
Thank you very much.